Here's problem sac219n3. If you haven't already read it, you might want to pause here and read it. We're going to jump right to part A, find the average EMF in the loop. I've gone ahead and drawn a before and after picture. Here's the loop while it's fully in the magnetic field, but moving to the right, moving out of it, and in the after picture it's just completely out of it. This is at time t equals 0 seconds, and here at time t prime, which is equal to 0.20 seconds, as stated in the problem. We're also given that the area whose perimeter is defined by the loop itself is given as 0.36 meters squared. Now, I want the EMF, that's script D. What we've generally talked about most of the time in class is that if you got a changing number of magnetic field lines through a loop or coil, and we've got that here, the number of magnetic field lines through the loop is decreasing with time because we're moving that loop away from the magnetic field. But in such cases, according to Faraday's law, when the magnetic field is changing, you get a current induced in the loop. And when we state it that way, we're skipping the middleman associated with Faraday's law of induction. Another way of stating it is that when you change the number of magnetic field lines through a loop or coil, as that is changing, there is an EMF induced in the loop or coil, and that in turn causes a current. Remember, a battery was a seat of EMF, or a power supply, so it acts as if there's a battery in the circuit. And the EMF, let's take a look at your formula sheet. In magnitude, and we're going to only worry about the magnitude, the direction we'll get by the right-hand rule, but in magnitude, it's the number of turns in the coil or loop, and in the case of a loop, there's only one turn, so n is equal to 1. Just think of n is equal to 1 in our case, and we can ignore that n. And then the flux here, this expression represents the time rate of change of the magnetic flux, where the flux itself, conceptually speaking, is just the number of magnetic field lines passing through the loop or coil. And in that expression, we can, making up the flux is expressed as the product of B times A, where B is the magnetic field. We've talked about the idea that in a magnetic field diagram, the closer together the lines are, the stronger the magnetic field. That's how we convey in a diagram the strength of the magnetic field. So we can think of B itself as the magnetic field line density, and then when you multiply that times the area of some region through which that magnetic field is passing through, you actually get what is conceptually speaking the number of magnetic field lines, or what in actuality technically is referred to as the magnetic flux. So we multiply magnetic field line density times the area to get the total number of magnetic field lines, conceptually actually referred to as the flux, and then find out how much that changes in the 0.2 seconds corresponding to the process. So let's get the initial and the final flux first, then we'll be able to see how much it changes in that 0.2 seconds. The initial flux, I'll just call that phi, is that constant magnetic field times that area that's enclosed by the loop in the before picture, and that's going to be 0.015 Tesla times the area enclosed by the loop, which is 0.36 meters squared, or phi. I'm just using the symbol phi. You can use a subscript B if you want to emphasize that it's magnetic flux rather than, say, electric flux. But I get for the flux in the before picture just 0.0054 Tesla meters squared. And in the after picture, I'll call that phi prime. To be consistent with your formula sheet, I'll go ahead and put that subscript on there. Phi sub B prime is just 0 because there is no magnetic field passing through the loop or coil in the after picture. So the delta phi, well, it runs from 0.00, it changes from 0.0054 Tesla meters squared to 0 for a change of negative 0.0054 Tesla meters squared. So delta phi, go ahead and erase that, delta phi is minus 0.0054 Tesla meters squared. And then for script E, I just understand that we're only getting the magnitude here, especially when I emphasize that on the right I'm going to use the absolute value sign. So we get delta phi divided by delta t, and the time interval over which this occurred was 0.20 seconds. I can put the minus sign in there. It doesn't really matter since I'm dealing with an absolute value. I'll go ahead and copy it down just as we calculate it. Divide that by the 0.20 seconds, and we got the EMF in magnitude induced in that loop is just 0.027 volts. I think that's the answer to part A. Let's see if that was indeed the question. Find the EMF. Okay, yeah, we got the EMF. Then B, they want the average current in the loop. Alright. This EMF, it's induced in the entire loop, throughout the loop, but we can model it as if it was a battery, just for that 0.20 seconds, as if it was a battery. Furthermore, the entire loop altogether, that length of wire has a certain resistance. It's got a certain resistance per unit length, and the total resistance will be its resistance per length times that total length. Well, we can model that as if it was a perfect conducting loop with a single resistor in it. So I'll model the EMF as if it was a battery. And it's called lumped components model. Lump all the resistance of the entire loop into one resistor right up here, where the R is equal to 1.5 ohms. Now, I've chosen that battery direction arbitrarily. I can make this side longer if I have to. Let's see which way the current is actually flowing. According to this model, it's going around that way. Let's see. We got changing magnetic field produces a current by Faraday's law. It induces a current in that loop. The induced current produces its own magnetic field by Ampere's law. And by Lenz's law, the new magnetic field is going to be in that direction, which tends to keep the number of magnetic field lines through the loop the same as what it was before in the same direction. Okay, before we had a whole bunch of them in the downward direction. What's happening is in the after picture we got none through it, so we're losing downward directed magnetic field lines. To make up for that, we need for the magnetic field produced by the induced current to be directed downward. So I call that B pin, and it's in the downward direction. Now, in order to produce B pin downward according to the right hand rule, the current has to be clockwise as viewed from above. That is, if we point the thumb of our right hand in the direction of B pin, the fingers of the right hand curl around in the clockwise direction from our vantage point, which is the top view. So I was right. This was had a 50-50 chance, and I guessed right. So the current will be going around this way in our lumped circuit element model of the loop. So we treat all the resistance as being at one location, all the voltage at being at one location as if it was a battery, and experimentally we find that you get the same results as you do for the actual case where the EMF is distributed throughout the loop as is the resistance. So the battery voltage in this model, same as the EMF being induced in the loop, that's the 0.027 volts. Okay, now we got a very simple circuit. We recognize that the voltage across terminals of the battery is the same as the voltage across the resistor, so we can use Ohm's law. V is equal to IR, with R being a constant. In this case, the the voltage across the resistor is that script E. Solving for I find it to be E over R. If I substitute the given values, 0.027 volts and 1.5 ohms, I find that I is 0.018 amperes. 0.018 amps. And that wraps up part B. Now on to part C. Find the total charge passing any point in the loop. Okay, if you got a conceptual understanding of what the current is, then this should be easy. That is, they want the total charge passing any point in the loop. So I pick an arbitrary point, for instance, that one indicated right there, and I want to know how much charge passes that point in the 0.20 seconds during which this process occurs. Because after that, the loop is completely out of the magnetic field and no more charge flows. Well, current by definition is the charge flow rate. It is the number of coulombs of charge per second passing at any given point in the circuit. So the total charge is just going to be the number of coulombs of charge per second passing any given point times the number of seconds, I call it delta T, during which this charge flows, and that'll be the 0.018 amperes, which is the same thing as coulombs per second, times, oops, you got 0.018 there, don't forget the decimal, it's 0.20 seconds, for a total of 0.0036 coulombs. Alright, let's see what's next. Part D. Find the average power dissipated in the loop. Okay, in our model, that's the rate at which energy is dissipated in our resistor in the lumped circuit, although in reality that's distributed throughout the loop. And that's the rate at which electrical energy is being converted to thermal energy in the loop. And you do have an expression for that on your formula sheet, that P is equal to IV. That's the rate at which electrical energy is converted to thermal energy, and a resistor is the product of the current through the resistor and the voltage across the resistor. So let's just copy that down as is for part D at first. P is equal to IV, and then of course the voltage across that resistor is just the script E, 0.027 volts. And the current we just found to be I wanted to write that. That's I, same thing as I times script E. And then 0.018 amperes is what we had for the current, and the voltage 0.027 volts for a power of 0.000496 watts. An ampere volt is a watt, and I'm going to round that off to 0.00049 watts. And then see what they want for part E. Find the total energy dissipated in the loop. Okay, again, this calls for a conceptual understanding of power. Power is the rate at which energy is being dissipated, the number of joules per second of energy being dissipated in the loop to find the total number of joules of energy dissipated in the loop during the 0.20 seconds, then I just multiply that rate at which energy is dissipated times the time, and I'll get the total amount of energy. So it calls for a conceptual understanding of what power is. That'll be the 0.000, I'll use the original value there and we'll round later, 486 watts, or remember that's a joule per second. A watt is a joule per second, times the 0.20 seconds. So of course the seconds cancel out. I guess you just get energy in joules, and I get 0.000972 joules, or to 2 sig figs 0.0097. Writing out the word energy so that we don't mix it up with EMF, script E, or with electric field strength. F, this problem just keeps going on and on. Find the direction of the current in the loop. Well, we already did that. We used Lenz's law. I'll make a quick check on that. Field lines are decreasing in number, and they're downward. To make up for the disappearing downward directed magnetic field lines, I need a downward directed mag field line for B pin, and then by the right hand rule, if I remember to use my right hand instead of my left hand, I get a current which is clockwise as viewed from above. Thus, end the solution to problem